Hey guys, in this video I'm gonna show you something about supremum and infimum. So we'll first talk about its definition, and afterwards I hopefully will talk about the properties and its application. And I'll also upload some exercise after the video. So if you are interested in it, you may try to solve these problems. That won't be very difficult because it's just a simple ideas about supremum and infimum. So now let's get started. I'm not sure if you guys are familiar with the concepts of bounds. So I'll just quickly mention it because it's very straightforward definition. So, say we have a set A. What is the bound of a set? Actually, we have a lower bound and upper bound. So we'll just talk about the upper bound because it's pretty much the same for lower bound. I'm sure you will all get to the point of that. So what is a upper bound for a set A? If we say set A is 2, 3, and 2 and 3 are not contained in the set A, you may say that 100 is an upper bound for the set A, right? Because an upper bound is something that bounds the set from above. Bounds the set from above. So I'll write it down. A bound or a value or a number or whatever that bound the set from above. So it's true that 100 is an upper bound for the set A, 2, 3. But you can also find that 3 is also an upper bound of the set, right? Because if you take any number in the set A, 2.5, it is always smaller than 3. So 4 or 5 or 20 or 10 to 8, they are all the upper bounds of the set A. So you may also find that the upper bounds of a set may be infinitely many, right? It's not unique in most cases, but it's similar for lower bound. So I'm not gonna still explain it. I'm sure that you guys will get into that point. So now let's move on to the supremum and infimum, the concepts of supremum mainly, because the infimum is pretty much the same. What is a supremum? I actually like to say that supremum is something that furthers the definition of an upper bound or a lower bound if we are talking about a infimum, right? So suppose we have a set A, and we're assuming that A is an empty set. It's not an empty set. I'm sorry, it's not an empty set. So we say alpha is the supremum of the set A if it satisfies two conditions. The first is that alpha is an upper bound for A, and it's just like what we just said before. The upper bound for the set A can be infinite many, but I also mentioned that the supremum of a set is something that go further than the upper bound. So alpha should also satisfy the second condition, which is that alpha is the least upper bound for A. So it's like you can get all the upper bounds of A and you find the least one, the smallest one of all these upper bounds. Then this alpha is actually the supremum of the set A. Still, we're gonna take some examples. For example, we take 2, 3, the set 2, 3, but now 2 and 3 are all contained in the set A. What is the supremum of A? Well, first, let's say it's upper bound. So upper bound should be larger than every element of a set, right? So actually, you can find the largest element in the set A, but it's not necessarily. sometimes you cannot find the largest element in the set. Like for example, the set B, you cannot find a largest value or largest element in set B, right? But if you can find it, that's cool. That's pretty good. So the largest number in the set A is 3, and an upper bound should be, so the upper bound should be like larger or equal to 3, right? Like 3, 3.5, 3.7, 4, or something, or 100, or something more than 100. But you need to find the least upper bound. So that is to say 100, no, because we can find 4, right? 4, no, it's not the supremum. 3.7, no. 3.5, 3.1, 3.0111, no. The least upper bound of the set A is just 3. So, in this case, the supremum of A is 3. And as I said, the infimum is pretty much the same. So, you can actually think a little bit about it. What is the infimum of a set A? So it's still the same process to find the infimum. First, you can try to find some lower bounds for the set A. So, in this case, it's pretty simple. Because you can find the least. You can also find the least number in the set A, right? 2 is the least number, and you have to pay attention that the infimum is the largest lower bound for A. This is something that you need to pay attention to. Largest lower bound. So if you are trying to find the infimum of a bound of a set A, first you have to make sure it is a lower bound for the set A, and also it is the largest lower bound of the set A. So for supremum, it's the least upper bound, and for the infimum, it's the largest lower bound. So pay attention to that, because sometimes people just get confused. And still, let's in the example set A we're just talking about. 2 is like the least element in the set A, and you can actually find like 2, 0, minus 1 or minus 100, many lower bounds for A, but the largest lower bound is 2, right? So the infimum of A is 2. You can also try something more challenging like B. The supremum of B. Now you cannot find the largest element of B, right? But if you take 3, for example, 3 is definitely an upper bound for B, right? And can you find something smaller than 3, but it is also an upper bound for 3? You may think about these questions, because you are like trying to find the least upper bound for B, and now you are trying to prove, or you're trying to figure out if 3 is the least upper bound. So how can we do that to find something? So now the problem is that how can you figure out if a number is the smallest element that among all the candidates? So one way to show is that you try to find that there is no other smaller number than the number that you want to prove to be the least number. So in this case, I'm claiming that 3 is the supremum of B. So what I'm saying is that 3 is the least upper bound for B, which means, so we claim 3 is the least upper bound of B. BD is abbreviated for bound. We try to show that there is no smaller number that is also an upper bound for B. But by contradiction, we suppose there is a smaller number, and it is just the supremum. There is a number. There is a number like there exists C, a number C, which is contained in R. Is a real number, and C is the supremum of B, which means C is the upper bound of B, and C is smaller than 3, right? But by the density of the real numbers, if C is smaller than 3, then there must be some numbers between 3 and C, a number D, a real number D, between 3 and C. That means D is not an upper bound of B, right? Because you have some numbers D. D is smaller than 3, which means D is contained in the set B. And D is larger than 3. D is larger than C. So C cannot be the upper bound. In this case, we prove that there cannot be a smaller number among all the candidates, smaller than 3. So we prove that supremum of B is just 3. And the infimum is the same as that in the set A. The infimum of B is also 2. And what about C? Now C is the set of all numbers 1 over n, and n is all the natural numbers. We can list some of the elements of C, like 1 over 2, 1 over 3, blah blah blah. So, as you see, when n gets larger, I shouldn't say infinity. When n gets larger, the element of say 1 over n become smaller and smaller, and it somehow gets closer to 0, right? And in fact, when n goes to infinity, 1 over n converges. Well, you are not given the definition of converge, but it's just 1 over n is becoming closer and closer to 0, to the number 0, and it almost equal to 0, but it's not. It's just getting closer and closer. So actually, the infimum of the set C is 0. Still, you can use the method that I just talked about to try to figure out if 0 is the lower bound of the set C. Use the similar method I just talked about. Suppose there is a larger number that is a real least lower bound of A, and then you prove that it cannot be true. Then you will finally get that 0 is the infimum of the set C. And what about the supremum of the set C? It's pretty simple, right? Because the elements in C is decreasing, and we already have the largest number of C. It's 1, and the supremum of the set A is just 1. D is an exercise left for you. It's very simple, and actually, I think it's simpler than the third case. So what is supremum and infimum of the set D? You can try to find out. It's very simple. Okay, now let's move on to the property and the consequences of supremum and infimum. So now we are given a set A and it's not empty as before. Now here if A is bounded from above, then it is true that there exists the supremum of A. This property, I think, is pretty much straightforward because the condition for this property is just the first condition for the definition of supremum, right? A is bounded from above, so so that is to say you can find some upper bounds for the set A, and if that is true, it promises you that the property promises you that there exists the supremum of A, so you can always find the least upper bound of all the candidates, which can also be explained like the set of all the upper bounds of the set A will always have a least candidate, right? Because you are given a lot of upper bounds of set A, and you are trying to picking out the least one. And now the property promises that you can always find the supremum. So that is to say you can always find the smallest one of all the upper bounds. Okay, it's pretty straightforward. Now let's see the consequences of the set A. The consequences of supremum. Okay. Now alpha is the supremum of A if and only if, well, the double F here means if and only if. If and only if. Well, two conditions, also two consequences, right? If and only if alpha is an upper bound of the set A, and the second is that for any epsilon larger than 0, there is always an element of A, such that alpha minus epsilon is smaller than the element A. Okay, now let's see it from an example. Okay. So suppose the set A is 1, 7, and neither of the endpoints are contained in A. Well, it's easy to see that 7 is just the supremum of the set A, right? So 7 equals supremum of A. Then it says that so what we are doing is that we are saying the consequence from left to right. So now we already know that 7 is supremum of A. Then we will say that 7 is an upper bound, right? It's pretty simple because if it is a supremum of A, it must be an upper bound of A, right? 7 is an upper bound. It's straightforward. And then second is a little bit tricky. It says that for any epsilon larger than 0, there exists an element A, such that alpha minus epsilon. Well, let's see. Here 7 is alpha. So alpha minus epsilon. Let's say epsilon is like this. This much is epsilon. This is alpha minus epsilon. You can always find some element in A such that the alpha minus epsilon is smaller than A. And it's true, we can find like here, this is A lies in alpha minus epsilon to 7. So we already find one, right? And actually you can take any epsilon, like here, then this is alpha minus epsilon. And still you can find some element in A, right? Or if you take epsilon very small, string extremely small, like this, you will always find some epsilon. You will always find some element A that is contained in the set A, capital A, and satisfies this condition. So what about we move it from the right to left? So we are given, it's like we're given two conditions, and we will try to prove that such kind of alpha that satisfies these two conditions is just the supremum of A. So now alpha is an upper bound, and we're going to show it's the supremum of A. How are we going to show that? We not only know the concept of the supremum, so we have to show that alpha is the least upper bound, right? So we are basically try to show alpha is the least upper bound from the second condition. So still we are trying to figure out alpha is the least upper bound. How to do that? It's just what we just mentioned about, right? We claim, not claim. I'm sorry. We do it by contradiction. We say that we suppose. Suppose there exists a beta. We suppose beta is the real supremum of set A, and beta is smaller than alpha. But alpha already satisfies this condition, and we are trying to show that it's not possible that beta is the supremum of A. Sorry. So we are trying to show that the claim is not true, is false. So let's go and do this. Let's start doing this. Okay. Now well, from this condition, we say that since beta is less than A, beta is less than alpha, then we have beta actually is equal to alpha minus epsilon. Epsilon. I mean, you can find some epsilon such that alpha minus epsilon equals beta, right? Because beta is smaller than alpha. But we've already know that epsilon is from this we can from this equality we can say that epsilon is equal to alpha minus beta, which is larger than 0, right? Because alpha is bigger than beta. And from this condition, we say that for any epsilon larger than 0, and this epsilon we take is satisfies the condition that it's larger than 0. So there exists an element in A such that alpha minus epsilon, which is equal to alpha minus beta, which is equal to beta, is smaller than A. So we are saying that beta is smaller than A. But what we suppose is that beta is the supremum of A, and A is contained in the set A. That is to say, beta cannot be the upper bound of the set A. So beta cannot be the supremum of set A. So we now prove that alpha should be the supremum of set A, right? It's just the same method we just talked about by contradiction. We assume that there exists a smaller number that is the supremum of A, and we show that it's not possible. It's not gonna happen. Okay, so this is mainly what I want to talk about, the property and the consequence.